Good afternoon, ladies and gentlemen. Jamie here from Excel Point. So there's still a few people logging on. So we'll give it a couple more minutes and we'll kickstart in a couple of minutes once we've got more people on. Okay, right. Good afternoon, everybody. Thanks so much for your time and joining us on this second session looking at the ZYNQ UltraScale Plus MP SOC and how to build a basic system. With me on the call today, so I'm Jamie Pegg. I look after the AMD ZYNQ product line here at Excel Point. So Excel Point is a AMD ZYNQ distribution partner, along with a number of other product lines. Christoph Hayert is our applications engineering manager who will be conducting the training today. Alongside me, I have Ali Bator, who is our ZYNQ business development manager in Australia. I myself am based in New Zealand. In the interest of sort of time, we have muted the audience. So what we have made available is the chat window, but please use the Q&A chat window rather than the chat window. The chat window has been disabled, so please use the Q&A chat window. Here, somebody has asked the question, is this going to be like the last one with the chat disabled and only questions via Q&A accepted? Just curious. So yes, that's the same setup. So if you have questions, if you can use the Q&A window, that way then it stops questions going out to everybody and everyone seeing, kind of everyone's details and what they're interested in, that kind of thing. But we will, any questions that come through, we'll highlight those at the end so that if there's any questions that we feel everybody will benefit from, then we'll share those along with any answers. Without further ado, Christoph, if you want to kick into it. Yeah, okay. There you go.
Thank you, Jamie. Welcome everyone again to the second webinar in the series around the ZYNQ UltraScale Plus NPSoC. So during the previous session, we exported the hardware from within the Vivado design suite, and today we're going to use that generated hardware in Vitis SDK to build and run some bare metal applications on various processes in the PS. So if we look at our built hardware in the Vivado design suite using IP Integrator, we had exported the hardware by simply doing the export this way. We now have an XSA file ready to go, sort of in the output directory. If you recall, we also added a system ILA to be able to, an integrated logic analyzer, to be able to monitor AXI transactions. So what we are going to do today as well is we're going to build a small software application on one of the processors, which will issue some transactions to this GPIO module. And then at the same time, while the software is running, while the processor is running, we can monitor these transactions sort of going into the AXI GPIO block. So that's something we'll do as well today. So if we look at the same diagram that was shown in the previous session, we are now here at this stage where we handed off the hardware, and this can now be imported in Vitis for further software development. Before we are going to do that though, today we'll talk a little bit about the Vitis SDK and what a typical software application flow looks like on the MPSoC device, because as they are heterogeneous devices which include multiple processors, it's quite important to understand how these are structured within the Vitis SDK. So let's get started. ZYNQ provides the Integrated Development Environment IDE, which is part of the Vitis Unified Software Platform. The Vitis IDE is designed to be used for the development of embedded software applications targeted to ZYNQ's embedded processors, and it works with the hardware designs created with the Vivado design suite. It's built upon the Eclipse open source IDE, which is Java-based, which enables you to run Vitis both on Linux and on Windows. As some of you may be aware of, maybe having worked with Eclipse before, it is an extensible platform which enables you to customize the environment for a specific set of tasks and supporting these tasks with the necessary backend tools. ZYNQ has done the same, I suppose. So it has enabled ZYNQ to add new capabilities to support the Vitis IDE design environment. These capabilities make developing code for the SoC families easier and include a collection of commonly used templates for first-stage bootloader, C and C++ applications, specialized firmware, board support packages, and more. Another feature of is the platform-oriented development, which enables you to develop large and complex applications targeting specific processes or a group of processes within the hardware. ZYNQ has extended the capabilities of the Eclipse project to include all the tools to successfully and efficiently develop the complex software for ZYNQ's products, including the MPSoC devices. So these systems require at least one, sometimes two bootloaders, platform management software, and one or more user applications. And managing all of these aspects can become tedious and error-prone. The Vitis environment aids with that by automatically building makefiles that are intelligent enough to identify the targeted processor and invoke the proper backend toolchain. You can customize these makefiles to include options for building an executable tailored to your application. The tools interface seamlessly with the hardware and do not only support processors in the PS, but also any soft-core processors in the fabric, for instance, another microblaze. Profiling and other visualization tools are also included that help you understand the relationship between coding style and runtime performance. The system debugger is a capable debugging tool, and it's based on the target communications framework. And the tool communicates with the JTAG cable and connects the hardware to the various software tools. The traditional GNU debugger tool, GDB, is also still available, but it's nowhere near as capable as the system debugger. So it's recommended to use the system debugger as it's capable of debugging multiple processes, which is a requirement in multi-processor environments. Some of the Vitis IDE features include a feature-rich C, C++ code editor and compilation environment, project management, application build configuration and automatic makefile generation, error navigation, simultaneous multiprocessing debugging, processor debugging, sorry, source code version control, system level performance analysis and profiling, specialty tools supporting the programmable logic, bootable image creation, flash programming, and the command line, scriptable command line tools, XSCT. The Vitis tool focuses on full platform support rather than just a collection of applications that you must manage manually. So the tool organizes information into projects. Some of these projects are pure software, while others include both software and hardware elements. We'll discuss all the project types in the next couple of slides. So while the Vitis IDE does do a good job of limiting the amount of information, it can become quite intimidating when you look at it for the first time, as there is not really a start here flow to start with. So we'll discuss the setup in a little bit. But let's review the application development flow in the Vitis IDE. So as already said, before the software development can begin, we need to import a hardware specification file. We created our own now during the last session with the Vivado Design Suite, so we'll be using that today. The Vitis IDE then uses this hardware information as a key component in a platform project. As mentioned during the last session as well, the hardware description enumerates the number and types of processors, memory capabilities, available peripherals, address ranges, etc. Sometimes though, especially in a parallel workflow, it's desired for software developers to start software development before the hardware is finalized. The MPSoC contains processing systems complete with heterogeneous processors, peripherals, and memory, and these platforms are offered as predefined hardware configurations. So you can either choose to start development using built hardware or using a predefined hardware configuration, so that you can run things in parallel. All the Vitis environment projects are contained within a workspace. The workspace holds the developer's projects, organized into project directories, and a meta file that helps the development tools manage the projects and preferences. Once the workspace has then been defined, a platform project is created. Now, this platform project is the basis for all software development, as it contains the description of the hardware and the necessary boot projects. So the platform project contains two aspects. One is the hardware description and the other is the software description. So again, the hardware description is the imported hardware or XSA file. I mentioned last session as well, we will be talking about the XSA file a lot. Or if the design is not ready, one of the predefined hardware descriptions can be used. The software aspect is partially described by a domain. Now, a domain describes a processor or a collection of processors and the board support package or the operating systems running on them. Boot components such as first stage bootloader or platform management firmware are automatically generated within a platform project. And then application projects exist in other types of projects and application projects. So application development is nothing else but the process of writing your user code. Numerous templates are available to help you get started. They're quite powerful for validating the behavior of the underlying hardware, as well as starting off as example designs. So applications then are also populate the system project. So this is also a new concept. The system project describes all the simultaneously executed applications. With the applications and supporting projects then built, the code can be downloaded to the board for testing and validation. This can be done using JTAG or by using one of the boot flash devices on the target hardware, such as QSPI or SDCAT. But let's discuss this into some more detail. We've talked a little bit about what a platform project is, a domain, a system project, but let's discuss this in a little bit of more detail. So let's start with the workspace. The workspace refers to a physical location on the drive where all of the Vitis SDE files reside, regardless of the type. The location includes a metadata file for remembering your user preferences and a directory for each project. The workspace simply enables navigation among the projects without having to locate the project directories in the file system. The directory structure in each project directory is dependent on the type of project that the directory contains, and it contains both user and tool generated files. Multiple workspaces are also supported. However, just to note that they're all independent of one another, and they can only be active one at a time. Platforms are a new concept introduced with the Vitis IDE. To put it simple, a platform or a platform project consists of the description of the hardware elements and the software to boot and maintain the platform. These include the processor cores, memory controllers, and peripherals both within the PS and the PL. So the XSA file contains a description of the hardware. And if a modification is made to the hardware, the XSA file can simply be re-imported in the Vitis IDE tool. So you don't need to create a new platform for it. You can just update it. So if changes affecting the processor systems are detected, all other files that are directly dependent on the hardware are rebuilt. The platform project is customizable as well for adding domains or modifying domain settings. And one or more domains or board support packages can be based on one and the same hardware specification. So what is a domain? A domain is the principal software element that's found within a platform project. So the domain controls either a single processor or a group of isomorphic processes in the case of an operating system design. So a domain can contain either a board support package or an operating system with a collection of software drivers. So a board support package is the same thing. It's a collection of libraries and drivers that support the selected processor, and it's most closely associated with standalone applications. So this type of board support package is considered to be a single-threaded operating system. So in other words, an operating system without a scheduler, and that's able to run only one task. Multiple processes can be clustered and controlled by a single operating system. This configuration can also be represented as a domain. And then an application is assigned to a single domain, but that domain can be changed if necessary for that particular application. And then a system project is a container that collects all the applications that are active at a single time across all the domains. Multiple applications can reference a single domain across multiple system projects as well. However, again here, only one system project can be active at a time. When an operating system is employed, then multiple applications can be included in the system project because the operating system does contain a scheduler and context swaps applications, giving both the appearance of concurrent executions and actual concurrency. This is not the case with standalone applications because there is only one thread running. Only one application can be mapped to one single domain. Now, the beauty of a system project is that it's not focused on getting one executable onto one processor, but rather getting all executables and supporting code onto the platform, which can consist of a number of processes. A software application project consists of one or more source files and their headers. This is the realization of your design goal and can be constructed by compiling the project into a single executable binary, such as an L file. The application project is attached to one domain at a time, but that domain can be switched if desired. So this example, this diagram here only shows a platform project with one system project and one domain. Finally, the boot components are part of the software aspect of the platform. This section contains all the supporting elements necessary to bring up and manage the platform. So it includes the first stage bootloader and, where appropriate, platform management firmware. Now, these are automatically, when you create a platform project, these are automatically generated. So it reduces your workload, and you would not necessarily need to focus on these aspects unless either one or both of these applications need customization. So this slide here shows a slightly more complex setup where you have a platform project, but consisting out of 3 system projects. So the first system project contains 2 standalone applications. One application is based on domain 1, targeting the Cortex-A53 processor. The second application is based on domain 2, targeting the R5 processor. The second system project contains just 1 application, which is also based on domain 2, targeting the A53 processor. Now, note that no 2 standalone applications from the same processors can sit in the same system project, but 2 Linux applications can. So see here, standalone application 1 and standalone application 2 cannot be assigned to domain 1 for that particular reason, because it is standalone and it's kind of like single-threaded OS. So they need to be separated out across 2 system projects. So as you see here, the platform project has 3 domains as well, each targeting a different processor. So we've got a Cortex-A53, first one here, a second one here, and then an R5 processor. So we've already discussed the application flow a little bit, a few slides back, but let's summarize this again, but then from a software perspective. So again, the Vitis IDE tool starts by importing the XSA into a Vitis workspace. Based on that, the platform is then created. Once the platform is set up, the next step is to create an application and a system project. Now, when you create the application project, it automatically creates a system project as well. So when creating an application project, you can choose, it'll offer you to choose a template, or you can just create a software application from scratch. After the application project is created, the project can be built, and then a series of ELF files are then generated. Once the application is on the board, it can be verified and debugged, and 1 or more applications from a system project can also be debugged simultaneously. When a system project is selected by running build, the Vitis software platform builds all the applications in a system project and creates a bootable image. The ZYNQ boot image format layout has multiple files, file types, and supporting headers to parse those files via bootloaders. Let's have a closer look at this flash image generation and the booting sequence of the MPSoC devices. I'm actually going to stretch out a couple of slides here because I think it's important for you to understand all the components that are loaded during a boot sequence, because typically people working with the MPSoC working for the first time tend to have issues with booting and the boot sequence. So I do think it's important to emphasize to stretch out a bit of time on this. So the flash image generator tool, or bootgen, produces a boot header, shown here in yellow, which is read by the first stage bootloader, and it is used as an index into the flash image. So bootgen is part of the Vitis IDE, but it can also be executed from the command line. So typically you just enumerate the input files, and then the bootgen tools generate the flash image. Each block or section of the flash contains yet another small header that describes the content of that block and other relevant information to successfully use that block's content. The first stage bootloader is the first program that's loaded by boot ROM, typically in the form of some on-chip memory, and it controls how the executables, bit streams, data are moved into the various memory devices. So multi-processor systems require this first stage bootloader application. And we also discussed this in the previous session. The first stage bootloader can run on either processor in the APU or the RPU for ZYNQ SoC devices. And its job is really to extract sections from the flash image, load those sections into various memories of the platforms at locations where the processors can find their code, and then command the processors to begin running from those locations. ATF, Trusted Firmware, is a special application that's loaded early in the boot process, and it supports the separation of secure from non-secure code execution. The second stage bootloader is an optional portion in the boot image, and it's used to load operating systems. Now, the first stage bootloader can't load an operating system, as operating systems are typically too big to run on-chip memory. So this second stage bootloader is effectively an application that is loaded by the first stage bootloader and passed to a processor for execution. The first stage bootloader can also load specialized firmware in the PMU on the system on chip devices. So we already discussed this a little bit as well. So platform management firmware can regulate processors and other resources to be fully operational in a low powered state or powered down. Bit streams can also be loaded in the programmable logic from the first stage bootloader or from an application. Operating systems, user applications, standalone applications, and data files can also be included in the flash image, and each file must be designated to run on a specific processor. Hypervisors, they're a special type of software that abstract the operating system from the hardware and enable multiple operating systems to run on a single platform simultaneously. And then finally, a golden image can be part of the boot image as well, which can then be used for fallback. So how do all, or when, let me put it this way, when do all of these components load during the boot sequence of an MPSoC device? Let's explore this a little bit. Remember those two triple redundant microblaze processors we discussed during the previous webinar? Well, they're pretty much used for the PMU by the PMU and the CS. They're called the PMU and the CSU. So the platform management unit and configuration security unit, they manage and perform a multi-stage booting process. So the MPSoC can be booted in either secure mode using an authenticated boot image or a non-secure mode using an unauthenticated boot image. And the boot sequence at a high level can be divided into three main boot stages. The first stage is the pre-configuration stage, which is controlled primarily by the PMU that executes PMU ROM code to set up the system. It also handles all the reset and wake up processes. The second stage is the configuration stage, where the boot ROM, which is part of the CSU ROM code, interprets the boot header, which is responsible for loading the first stage bootloader code for the PS into the on-chip memory. Here, both secure and non-secure boot modes are supported. Through the boot header, the first stage bootloader is then executed on either RPU or APU, whatever you've assigned to it. The third stage is then the post-configuration stage, which is after first stage bootloader execution starts. Here, the CSU ROM code is then responsible for system tampering responses. The CSU hardware in the background continues to provide ongoing hardware support to authenticate files, configure the PL, store and manage secure keys, and decrypt files. So while these are now three main configuration stages, let's have another closer look at this in sort of like a boot flow chart. So the first thing that happens is the PMU wakes first, and it waits for the power on reset to be assert. The PMU begins execution from the PMU ROM, and the first task it performs is to look at the 3 pins that describe the boot source, which can be via JTAG, SD card, use by flash, etc. From here, the PMU will then check the eFuse bits and determine if safety and system integrity checks should be performed. If so, then these tests are run. Once those tests are completed, the PMU will release the reset to the CSU. At this stage, the PMU will enter a low powered state in which it will remain until the PMU RAM is loaded with PMU firmware. Once the CSU is released from its reset, it begins execution from its ROM as well. It starts by checking the boot mode, which was read by the PMU, and initializing the processes associated with reading that device, including validating and, if necessary, authenticating the boot image header stored in the device. If the header indicates that PMU firmware is present, it's loaded into the PMU's dedicated RAM. The CSU then attempts to load the first stage bootloader into the on-chip memory. And if needed, the CSU will also run the decryptor and authenticator on the first stage bootloader. If it passes, it's executed by the designated processor. If not, the full-back boot sequence is loaded and ROM. Once the CSU has completed these tasks, it begins running the tamper protection code until the next boot occurs. So as mentioned, the first stage bootloader, it can run on either the APU or the RPU. So whichever processor the FSBL runs on, it'll begin configuring the PS and, if applicable, loading the PL. The PL can actually be loaded at several stages, so this is just the first opportunity. It's important to remember that systems that run on operating systems do need a second stage bootloader. The second stage bootloader is managed as if it were any other bare metal application. So it would then be up to the second stage bootloader. For Linux systems, this is just U-boot, to load the operating system from the appropriate non-volatile source, then pass control to the various processes to launch the operating system. So a little bit elaborate on this, but I do think it's important that you get a good picture on how this operates, because without a doubt, it's not uncommon for people to have issues during a boot sequence at some stage. Now, beyond the scope of these webinar series a little bit, but just so you're aware, and for people who are looking for a more automated flow at some point, Vitis also provides an interactive and scriptable command line interface to the Vitis software platforms, which you can also create everything that we're going to do within the GUI. And that's kind of where I think we can leave off on the slides. So what we'll do now is we're going to start using the Vitis IDE, import the hardware that we generated during the last webinar, and then demonstrate how to build the principal project. So the platform, some applications, some system projects. We'll also run some applications on a Cortex-A53 on an R5 processor. We'll maybe create a bootable image, stick it on the SD card, and then to boot from flash, sort of thing. So let's start playing around a bit. Sorry, this is
so Christoph, before you start going through this, I think this might be a nice kind of point. Maybe just there's a couple of questions that just popped through. Just wondering if you can maybe address those.
Okay.
So one question is if you know if it's possible to separate out user-generated file content from the tool-generated content, like, you know, thinking from a revision control system POV, you know, because obviously the ZYNQ tools, you know, do a lot. Just wondering if there's a way to kind of separate it out.
Yeah, so you could import, I mean, you could import remote sources. Yes, you could easily have you have your own libraries of C code maybe sitting somewhere, and yet, yes, you can import that and tie that in with your own revision control, I suppose, if that's the question.
Okay. And then another question that came through is roughly slide 11. When you were talking about the domain, you know, the domain kind of explanations and things is, could one A53 core run a standalone app, and then other cores in the application processor unit run Linux at the same time?
Yes, so that's what you see here in this example. So this is this is where the platform concept is quite new. You can have, it consists of multiple domains, and each of these domains can have their own board support package or even a Linux domain. So yes, you can run Linux applications on one Cortex-A53 and have another one just used as a standalone BSP sort of application. So yes.
So like, for example, like bare metal on one and operating system on the other kind of thing.
Yes, that's what you see here. Yes. Yep.
Yep. Cool. All right. Yeah, thanks for that.
So what we'll do today actually is we are going to create a number of system projects. We're going to create a number of domains today for the A53 and the R5. we won't do Linux yet. We will come back during the next webinar. We'll build all the Linux components such as the kernel, the U-boot, etc. But then we can use that in Vitis to build Linux applications in Vitis as well. But we can't do that until those components are ready. So we'll move that. That'll be for the next session. But we will build some applications in these two domains, some standalone applications today. So Linux is for the next session. So why don't we get started? So I had already opened the Vitis IDE. So here is the design perspective. Normally you'd have a welcome window as well if you open it the first time. I've already passed that, I suppose. So the first thing we need to do is create a platform project. So you can easily do that by File, New, Platform Project. Let's give it a name. Here it already is asking a platform project can be, well, telling me can be created from one or two inputs, from the hardware specification or from an existing platform. So if hardware is not ready yet, then software developers could still begin developing software by choosing a specification from an existing platform. But as we built our own hardware last week, during last session, we will import that. So I will browse to export it. It should be here. This is now reading the hardware specification.
So once that's, oh, sorry.
Once
yeah,
it's
sorry about that.
Am I good to go?
Sorry.
Okay, yep, okay, all good. So once it's read the hardware specification, it automatically completes these fields for operating system and processor. I'm going to leave it like that as that is, which is fine. It also just ensure that this generating boot components is checked. So it will generate the first stage bootloader as well as platform management firmware, as well as some other important code. So here is where you can select on which processor you want to run the first stage bootloader. I'm going to keep it on an A53, which is fine. So it's a standalone application on an A53. So it will create a domain for me on an A53, Cortex A53. So we can click finish. Sorry. Okay, so let's explore a little bit what's been created for us. So here on the left-hand side, we see a platform project. We can also see that there are some directories for platform management unit and first stage bootloader. So if you drop down here, there is a lot of code. But as mentioned, you don't really need to worry about this unless you wish to customize this. So in order to explore the platform settings, just double click on SPR here, that's platform settings, but it's already open here as well. And this is where you'll see the concept of a domain. So you'll have a domain on the Cortex A53, which has a first stage bootloader and a Cortex A53 standalone application. And then there is also the PMU's domain. In order to add a domain, you can simply click on the plus icon. Let's say we do R5. Actually, we might as well create that now. We could create a new domain. the standalone BSP, and here we can select our processors. So we just pick the R5, which is a 32-bit. So here we're adding a new domain. So all these board support packages, you'll see, will have imported libraries and drivers for all the peripherals that we have included in our block design and our IP integrator. So you'll see here already it has identified 2 AXI GPIO slaves. What is quite nice here is that you can import examples, and we'll do that shortly actually. So there are code examples available to import to start working away with. There is also direct access to the API from within. So this is a good way to have immediate access to documentation. So we'll see the AXI GPIO, and I think we had, if you recall, we had Ethernet on the GEM3. So there are a number of peripherals available already. There are the 2 UARTs, so you have access to, if you want to develop some UART applications, that's all handy in here. You can also modify these settings, obviously, some of the driver or libraries by clicking here. So for instance, if you don't have a UART and you wish to redirect output to the target communication framework, you could select core side here, but because we have UARTs enabled in the processing system, I'm just going to redirect it to an actual UART, which is fine. So now we have a platform project. So I'm going to put the slide back actually. A platform project with 2 domains, one on the A53, one on the R5. So I can now build this. I can either just click the hammer, or I can just right mouse click, build this. So also, if you further explore here a bit, you'll see what's been exported from Vivado. We have that XSA file, we have the bit stream, which had been generated, and that PSU initialization code, etc. Wait for this to finish compiling.
So whilst that's compiling, Christoph, one question that came through is, can we do a build of a Linux image outside of Vitis using Vitis CLI for necessary related elements, sort of in the context of having to, of having a custom build system, and the desire to import Vitis stuff into their build rather than importing their build into Vitis?
If you're referring to Linux kernels, root file, Linux kernels, or the Linux components to build an embedded Linux system, then yes, this is what we'll discuss in the next session with Petalinux. So to build a bootable Linux image, yes, we'll use the Petalinux tools, and you can build applications and everything with Petalinux, which can tie in with Vitis, but this is not the question maybe, or the question slightly different?
That's the question, yes.
Okay, so yes, it can be done externally. So this is why this Petalinux for Linux, this is what happens during the next session. So we'll come to that, and then at the end of session 3, it'll become clear how Vitis Linux applications and Vitis tie in with building Linux components using Petalinux.
Okay. And then, yeah, finally, sorry, one last question. While an application is running, can you use the first stage bootloader to load a new application that you uploaded into memory, and how would you do that?
Can you repeat that? Can you use
Yeah,
the first
so
bootloader?
while an application's running, can you use the first stage bootloader to load a new application that you upload into memory? And how would you do that?
No, at that stage, it's not the first stage bootloader anymore. Not the responsibility of the first stage bootloader anymore to upload that, I would imagine. I would need to double check that, but at that point, it becomes the processor's responsibility to do that.
Okay, thanks.
Oh, yes, I might double check that, but that's what I think. Yes. Okay, so now that's built. If there's no any other questions for now.
No more questions at this point. Thanks, Christoph.
So now that this is built, the next thing we need to do is build an application project. So let's do that again from the menu. We can select File, New Application Project. And now we need to associate that with a particular platform project. So here again, you could do it on a new hardware specification, but we already have one. We built the platform project here, which is on, this is still the correct part, yes. So here we can now select the domain as well. We have two domains, one's on A53, one's on an R5. So we will .53. Going to give it a different system project name. So apart from the application project name, it also asks you to name the system project. As mentioned, when you create an application project, it will also create a new one, or if you already have one available, then you can assign it to a particular system project. But we don't have one yet, so we're going to create a new one. It will run on the A53 processor. We'll just click next. Remember, we also still only have, if we run on this processor, we only have that standalone board support package. Click next. And now we'll be able to select a couple of templates, or depending on your application, you could choose the closest to your the template that matches your application the closest, but I'll just select a basic hello world application. We can select the template. Let's just say hello world. So here you now see we have one application project in the design perspective, but it also has it belongs to a particular system project. So now we have an application project, a platform project, a system project, and an application project. So if I just open the code, A53, something like that. Save that file, build this. Successfully built. So I'm going to turn on the evaluation board that I have here and set the boot mode to JTAG. That should be correct. I will turn that on. And now I'm going to just create a debug or a run configuration for it by right mouse clicking and just do debug as the debug configuration. So it's a single application debug. Add a new application, and here it's quite, you can kind of review the settings. So it's a standalone application debug which runs, so the name is hello A53. It runs on the Cortex A53.0 and the target setup is quite an interesting tab to cross check, because here you kind of see what happens. So first thing that happens is it resets the system, it programs a programmable logic. Now it's important to do this. Important to do this before you load your application, because imagine you program the programmable logic and these become active, but they send out something's not defined. It can actually lock up the system. So it's important that this is programmed before you run your applications. If the processor is trying to access something that's not available yet, or the other way around. So it also includes the bit file, which was the bit stream, which is imported. So we can now just debug that. So here we have the XSCT console where you can follow. We're going to maybe open up the COM port. I can open PuTTY, but I've got the serial terminal available here as well. So I should be hitting a breakpoint now shortly. Yep, so if I clear that, and now breakpoint set here. So that's a very simple application we now ran on the A53. Now, if you wish, what we can now do is, in order to simultaneously run some applications, both on the A53 and on the R5, we can, in the same system project, because we've got two domains, A53 oops, we have an A53 domain and an R5 domain. So those application projects would be possible to coexist in the same system project, as was shown here in this slide. So we have one system project, we have one standalone application that we now ran on the A53. We have a second domain, so we're going to place that second standalone application in the same system project. Let's go back to we'll create a new application project, again, in the same platform project. Click next. And we're going to run this on the R5. And we're not going to create a new system project. We're going to place it under the existing system project. Belongs to the R5 domain. Next. Again, we can just do something very, very basic. So now we see we have two application projects in one system project, but assigned each to a unique domain, different processes. In here, let's change that code a bit. Hello. Save and build. So if I now wish to run these simultaneously, you don't create a run or a debug configuration for the application project, but for the system project. System project debug configuration. I'll just add one. And then here you could actually select if you only wish to debug a particular application, because you could obviously have many. And then if you look at the target setup, so it's pretty similar, where it programs the programmable logic, runs a first stage bootloader, but now you'll see that two processors will have an application running. So one on the A53, one on the R5. So let me just debug that. bit of time. Must be late on a Friday afternoon. Okay. So we'll hit 2 breakpoints now normally because we've had 2. That as well. Oh, so there is our R5. And there is our 853. So we ran that in one debug configuration. So the next thing I'd like to show you is I'd like to create, so if we go back to our platform settings and we look at the port support package, sorry, that's for, what is it? And we have AXI GPIO. Remember, we had these 2 modules here. So what I'd like to do now is write some software that will actually write to this GPIO block and then monitor that, open up the hardware manager and monitor those transactions. So what I'm going to do is, if I click on import resource, import examples here, it's going to create an application project for me. Because I run it on this A53, it will create a separate system project for me, because remember, you cannot have 2 application projects on the same domain. So if I import an example, basic, it's created a new system project because these 2 are the same domain. I cannot have these sitting in the same system project. So it's automatically created a new system project for me, which is fine. So if I now just open up this example code, so it's pulled in some of the ZYNQ libraries, and it's just going to do some toggle some LEDs, I think. So what I'll do is, just to ensure that code's running, LED on, and then maybe LED off. I'm going to build this, save this, I'm going to build this, and create a new debug configuration for it. View the settings, it will run on the Cortex A53 0 as well, but standalone, and it's got the right application here. So I'll run that. And then while that's running, I'm going to open up the hardware manager, and then I should see my integrated logic analyzer pop up. And then I want to monitor those transactions that the processor is executing. Okay, so that program is now running. If I now open the hardware manager, you'll see I have my system logic analyzer, which looks pretty similar to a general logic analyzer, and I have my system ILA, my hardware ILA, my system ILA IP which is the one that we added in. So, and because it's an AXI monitor, it can monitor transactions, you have all the interface signals from your AXI master coming out, and you can pretty much probe anything. So I had already added 2 probes. So if I now want to say that my write valid on this bus, and if I now trigger on this here, then I'll see that the software is executing transactions, and I can debug that. So I'm now triggering on the write data, so it is toggling the LED, so I can trigger on both zeros and ones, I'd imagine. Yeah. So this is one way to debug transactions at a really low level. And where we're measuring now is obviously the monitor in here. So if you expand that, have all these signals on the AXI bus are available to us in the hardware manager. And so you can trigger on that. So the last thing I would like to show you during this webinar is how to create a bootable image. And load that bootable image and boot from the SD card. So here at the top level, the top menu, you can see ZYNQ create boot image ZYNQ UltraScale Plus. So boot gen is sort of underlying within Vitis. So boot gen is also available in Petalinux, but it's also available from the command line, and it's also available through the GUI and then the Vitis IDE, just in a different presentation, I suppose. So here you can see the boot image partitions. So we have, actually, let's create a boot image for that one, because then we can see 2 applications. Now we have the first stage bootloader, bit file, and tow bit stream. So what I also want to do is, why don't we just add the platform management firmware as well. So the file path should be, it's our project ZYNQ apps demo, it should be somewhere in here. Where export boot software. So there you go. So that comes with the platform project. You don't have to worry about it unless you wish to leverage the power management features of the ZYNQ UltraScale MPSoC. So I click open. This needs to run on the PMU, one of the microblaze processors. If I add this, it's up a bit. And then output format, if I change this to, where would I want to change this? Where would I want to put this? Boot.bin, we're going to boot.bin, create image. The file, that's fine. So if I now copy that onto an SD card, take out the SD card that I had already in there. So on my E drive, I'm going to maybe remove the one that I had on there, and I will take out the SD card out on my laptop. I will put it on the evaluation board and change the boot mode settings to SD card. Now, up until now, I had the serial COM port open here, so why don't I close that? I can also just open PuTTY Still. And if I now turn on the board, I have a first stage bootloader is running, the PMU firmware is running, and I have my two applications running, one on the R5 and one on the 853. And I think this is what I wanted to show you today. So I think we can conclude the webinar here. So, or the presentation at least. So during the next session, we will again start off with the same hardware description file exported from within Vitis, from within Vivado, and we'll then use the Petalinux tools to build an embedded Linux image from scratch. And then we'll also explain how the Linux components can be used in Vitis to build a Linux application, because all that entails is we would create a new domain, but we would then create a Linux domain here. And once we create that Linux domain, we would need to provide the boot components directory, which would then point to the output directory from Petalinux. And once that information is provided, you can start Linux application development within Vitis. But you can also do Linux application development in Petalinux, but we'll explain that during the next webinar. But for today, we've created some bare metal applications on various processors on the MPSoC system, showing you how to monitor some AXI transactions and showing you how to generate a bootable image on the SD card. So thank you for your attention. So I think we can open up or stretch out some more time for some questions. So feel free to answer some questions.
Yes, Christoph. So there's a couple more questions that came through. So with regards to flashing the FPGA bit stream, can the PL bit stream be flashed without initializing and utilizing the FSBL? And the next one is, if flashing the PL bit stream via FSBL along with initialization, is the programmable logic firmware persistent, or is it reloaded each time on power cycling the device? So I guess we could split that into two. Can the programmable logic bit stream be flashed without initializing and utilizing the first stage bootloader?
It can be loaded via Linux. So once your Linux operating system, or if you run Linux, is up all by a processor, by an application, you can load the programmable logic. No, it does not need to be loaded by the first stage bootloader. It can be loaded afterwards. The first stage bootloader is just the first opportunity to load it. So once you have your standalone application, or your board support your standalone OS or a Linux OS, then you can still use that to load programmable, or the programmable logic. Does that answer it? And what was the first question?
Yeah, so the first question is, can the PL bit stream be flashed without initializing and utilizing the first stage bootloader? Yes. And then the second part of that question is, if flashing the PL bit stream via the first stage bootloader along with the initialization, is the programmable logic firmware persistent? Does it stay there, or is it reloaded every time you power cycle the device?
Well, this depends on what you create in your boot image, right? So that's the BIF format. So let's see where I can find the BIF file. So in the bootable image format, that's where you define or enumerate all the components that will be loaded. So you can omit it from the first stage bootloader. So see here, for instance, so the flash image generator. So what we just did now is we added the platform management unit firmware. We added the bit stream. So I'm in the wrong place. you can remove that from the bootable image, and then the first stage bootloader, because it looks at all the partitions available in the boot image. If it doesn't find a bit stream, then it won't program it. But then it's your responsibility to do it afterwards via an application or via Linux. So you don't need Toad, but obviously at some point you need Toad. Does that?
Okay.
Yep.
Another question that came through. Excuse me. Can we run application 1 on the A53 and application 2 on the R5 and make them such that they can both access the same data? So for instance, both applications have access to the same data in memory. So application 1 can do some processing of the data, and then application 2 can complete the processing on the data. And how can both applications have access to the same memory? That's
Yes.
a good question.
No, it's a question that I've recently come across, and yeah, the answer is yes, but I need to go back into the documentation. So let me get back onto you on that. So whoever, I can't see you ask that question, but please forward the question to me in an email. I know where to find that information. I've recently come across it. And so yes, the answer is yes, you can. But off the top of my head, I've just forgotten myself.
And I guess, just for everyone's benefit, so I will list out questions asked with relevant answers. So I will arrange for that to be sent out along with the video links. So hopefully, that'll give everyone the opportunity to view the questions and answers. I have a couple more. Okay, so this one is, how can you load new code on a remote ZYNQ device that no longer is connected to a computer? So you can't take out the SD card.
The questions in to answer. How can you load new code? Well, what do you mean with is no longer connected to a computer, no longer connected to Ethernet, or so that you can't remotely perform a remote firmware upgrade through, like, floating around in space? Can you load a new? Obviously, yes. I understand your question now. Yeah, okay. Yes, I'm with you. Okay, you're not talking about a new programmable bit stream, right? Okay, okay, I'll need to get back to you on that. It's kind of, it seems the answer is the question. There's so many answers to that particular question. I think it's just maybe we need to take it offline and kind of try and understand what your application is, because there's many ways to load new code, I suppose. On a remote that no longer connected, you can't take it out. Yes, DCAT. Well, I think you'd probably want to boot from a different medium, right? And probably write to QSpy, or so that you can update the QSpy, which is permanent, and then yes, load it from QSpy, I'd imagine. So there's different boot media, I suppose, different places where you can yeah. and PS. It depends a little bit, I think, on what type of communication you have available as well at that point. So it's really a case of trying to understanding a bit more on what ability you'd have to upload new code onto the FPGA. What's going on? Okay, the questions have disappeared, I think.
Oh, sorry, that's my bad. If you have a look at the answered tab and scroll down towards the bottom, you'll be able to see you'll still be able to see the questions. But yeah, I think this one might be better done offline, so that
yes, I think we need to take this offline and understand how your FPGA would still communicate. And it might be a case of what if there is a wireless link, or you need to understand a little bit more what's available, because normally, yes, it's you can upload firmware remotely via Ethernet, via TCP/IP, and all of that. So it's kind of interesting to understand a little bit.
Christoph, just
yes.
think about a telecommunication system. There is a RF SOC, there is a telecommunication system, and you know, the FPGA is for this telecommunication system, and they want to, you know, change something in it actually. But it will affect the device itself. I guess this is such kind of a question.
Sorry, can you repeat that again? Sorry, I know you mentioned
think about an RF SOC for this device, and then it is a wireless telecommunication device. I think this kind of application is the question.
Oh, the question is how can you upgrade code?
The system itself is the telecommunication system. You have only communicate with these RF SOC, and you want to upgrade the system actually.
Yeah, I'm not. I need to understand this a bit more. Sorry, I can't answer that question right now, but it seems to me that in this particular, I know the case, I think, but in this case, I'm not sure if it's possible without understanding a little bit more around the infrastructure of what type of memory is available, what type of communication links are available.
Okay, let's contact later.
Okay.
Yep.
Any more questions? So we've had some interesting questions come through, and hopefully we've done our best to answer where possible. Some of them we'll have to get back to you on at a later stage once we've done a little bit of research. Yeah, any more questions? Oh, there's one. Can the bit stream be loaded from two sources? So my understanding is the bit stream can be loaded from like SD card, can be loaded from from quad SPI, from eMMC. But do you mean, can you expand on that question? Do you mean can the bit stream be loaded from two sources at the same time, or are you just looking at different ways to configure the device? The question is, can the bit stream be loaded from two sources
The answer to that question, I think, is yes. You can obviously implement various ways to load a bit stream, and there's no one way should not inhibit you from loading it in another way. So yes, you can always boot it from QSPI, but you can always, for instance, via Ethernet, upload it,
Yes.
stick it in a different medium and load that from another medium, for instance. Yes, so there's no, you can, yes, depending on how you wish to do this. Yeah. I don't think this platform is it for IoT, but maybe good. Two-way communication, you may.
So this one, I think we need to reach out after the fact, and maybe just get a bit more detail about the system requirements and things like that.
So I think the question is this platform for IoT or net? I think for FPGAs and IoT, I think is more. The problem there is, I mean, the challenge there is power consumption. I think. So the MPSoCs may leverage that with all the power islands, but the platform is most certainly suitable for network infrastructure, as well as for HD video and two-way communication and everything that's asked in the question.
Yes, it just depends, how much battery you've got, and and what the battery life is, what the charge life is, if it's like a shift life of 8 hours, that kind of thing. So understanding a little bit more about the application sort of requirements. I'll take a screenshot of this one and get back though. Okay. Any more questions? If not, oh yeah, here we go. Oh no, that's not a question, that's a thanks, guys. So yeah, you're welcome. Hopefully it was useful, and yeah, everyone have a lovely weekend, and we'll catch up again. When is the 7th, is it, Christoph?
Yes, it'll be next Wednesday.
Yeah, next Wednesday. But yeah, feel free to reach out if you have questions. We will send out the video hopefully a little later today of both the first session and the second session. And yeah, if you have any questions, then come back to us. Okay, on that note, thanks, Christoph, for driving that. And thanks everybody else for sitting through that, and hopefully it was useful for you. Okay.
Thanks everyone. Have a nice weekend.
Thanks, guys.
Bye bye.